Good morning, how y'all doing?
Morning.
Hi.
I'm here today to talk about quantum computing and computers and whatnot. First things first, let's talk a little bit about quantum mechanics. Now, quantum entanglement is where like two atoms are connected to one another, even like say one from the other side of the galaxy to here, and they still affect one another. If you looked at one was positive, the other one would be negative. When you look at one, it affects the other instantaneously. Superconducting is when you cool a metal like copper to temperatures close to absolute zero, and all electrical resistance goes to zero. They lose. Say you had one a mile long, theoretically, it would lose no, it would be as strong as one end as it would be the other. And it creates a magnetic field that lets other metals and other magnets levitate. So let's keep these two in mind and we're moving on. Classical computers use bits that are either 1 or 0. Quantum computers use qubits that can either be 1, 0, or in the supercondition of both. You can't look at a qubit because when you do, you try to measure it directly, it changes to either 1 or 0. So you have to measure it without looking at it. That's kind of hard in a way. Quantum computers can be used to better predict the weather, help make new drugs, and allow us to better look at the study between atoms and molecules in greater detail. And Google is looking at it to see if they can make better AI and whatnot. Google, NASA, and Lockheed all have a quantum computer. Lockheed was the first one on May 25th, 2011. They paid $10 million for D-Wave 1, and when D-Wave 2 came out, they paid $15 million. And on May 2013, they did Google and NASA purchased D-Wave 2 computer together. So they're working together. NASA is seeing how it works for now. See what it can do with it. D-Wave Systems Incorporated is a quantum computer company based in Verran, British Columbia, and Canada. Their computers, the prototype on February 13, 2007, D-Wave demonstrated the Verran system. May 11, 2011, D-Wave 1 came out with a 128 qubits processor. D-Wave 2 is installed at NASA labs. Has a 112 qubit, uses 12 kilowatts of power, cooled to 0.01 degrees Kelvin, or negative 459.63 degrees Fahrenheit. 100 times colder than outer space. Absolute 0 degrees Kelvin, or 459.67 Fahrenheit. D-Wave 2 comes with RF shielding from magnetic shielding, because when you make a quantum computer, it's very sensitive and it doesn't like outside noise, like radio waves or anything like that. So you have to keep it cold and you have to keep it the outside from interfering with it, but you have to interfere with it to do problems. We have D-Wave 3 is expected to come out this year. Both have a 1,152 qubit processor, however it is a 2,048 qubit chip with half of it disabled, and they plan maybe reactivating it later. Here what D-Wave 2 looks like. That's the main casing. Here what it looks like inside. This upside down waiting tape structure is all to cool this. That is the quantum computer right there. Little CPU quantum computer. How it looks like. I have a few videos to show you.
Of quantum computing. In addition to the universal model based on logic gates, which the Australian scientists have worked on, there are many others. One such model is the adiabatic quantum computer. The adiabatic computer was built by the company D-Wave, which was the first in the world to put such advanced equipment on the commercial market. This company, founded by Verran, Brownell, and Geordie Rose, began in the Physics and Astronomy Department of the University of British Columbia in Canada, but it later became an independent entity. The idea of building a quantum computer system was born out of the scientists' experiments with superconducting materials. The basic elements of D-Wave's computer processors are called SQUIDs, superconducting quantum interference devices, which are some of the most sensitive devices used to measure the intensity of magnetic field. In simple words, SQUID is a certain kind of superconducting ring divided by what is known as the Josephson junction. The superconducting materials that make up these devices have certain unique properties, thanks to which, at very low temperatures, nearing absolute zero, quantum uniqueness takes precedence over the classic principles of physics that we are accustomed to. For example, in the cooled superconductor, or SQUID, the phenomenon of electrical resistance does not occur at all. And due to a phenomenon known as the Meissner effect, some objects can even levitate. Unlike the single atom transistor, here, the form of qubit is the direction of movement of many united electrons, which, as a result of the low temperature and superconducting properties, may be considered equivalent to what, in the previous model, was the direction of the spin. In other words, here, zeros and ones describe the direction of flow of electrical current through the superconducting rings. The clockwise flowing current corresponds to 0, while the counterclockwise flowing current corresponds to 1. The entire computerization process in this type of model is based on the probabilistic method of what's known as quantum annealing. Quantum annealing consists of finding the optimal values among all possible solutions. The name of this method is derived from annealing in metallurgy, which is a technique of controlling the temperature of the cooled metal alloy. Slow cooling allows for the formation of ordered crystalline structures. In quantum annealing, the magnetic field is the equivalent of temperature. For instance, to find the lowest valley during a hike in mountainous terrain, we would have to trek across the terrain to finally arrive at the right place. Quantum mechanics reduces this search. Quantum tunneling is a unique phenomenon which allows the particles of the micro-world to cross the walls, contrary to the law of conservation of energy. Thanks to quantum tunneling, the electron searching for the lowest point in the given terrain would not have to cross it up and down, because it would have the ability to penetrate through those intuitive mountains, allowing for much more efficient searches. If the controlled variations in the magnetic field during this walk of electrons are sufficiently slow, then once the magnetic field is turned off, we should be able to arrive at the correct solution, which in this analogy would be the lowest point of the area. D-Wave's first client was an American armaments company called Lockheed Martin, which at the end of 2010 decided to purchase a 128-qubit D-Wave 1 computer for $10 million. In 2013, with the cooperation of Google, NASA, and URSA, D-Wave created a 512-qubit D-Wave 2 computer for an artificial intelligence laboratory. Researchers in this laboratory are using the D-Wave 2 computer to facilitate them in their work on and in areas such as the improvement of voice activation device technology, development of new drugs, climate change modeling, optimization of traffic control, development of robotics, and machine navigation and shape recognition. However, within the scientific community, there is a continuous and lively debate over the question of whether the computers manufactured by this Canadian company can actually be considered as fully quantum. One of the basic allegations posed by the critics is the possible absence of quantum entanglement occurring between the qubits comprising the D-Wave processors. However, according to most recent published scientific studies, the computer definition used by D-Wave is correct. Only time will tell whether this information is definitive. In order to take advantage of all that is offered by the fundamental laws of nature, we need software and algorithms, which are just as necessary as basic construction elements. Creating the algorithms, however, is a very difficult task, as it requires that we take into account the counterintuitive laws of quantum mechanics. Nevertheless, there are many people who have risen to the challenge. Peter Shor and Love Grover are the creators of some of the most well-known quantum algorithms. Most notably, since its creation, Shor's algorithm has generated a great deal of discussion among the scientific community, as it could be used to break modern encryption keys, such as RSA. If there were a quantum computer capable of efficiently using Shor's algorithm, the use of encryption, to secure bank accounts and other operations, and the accompanying difficulty of mass numerical division would cease to exist. Classic computers don't handle these type of difficulties very well, so we can sleep peacefully without worrying that our bank account will be cleaned out by a quantum hacker. Another significant algorithm is Grover's algorithm, which was devised to sort through information in unordered databases. Imagine searching through a phone book with a random assortment of names. In order to find a given telephone number, you would have to search through each and every listing, which would undoubtedly be cumbersome and time-consuming. However, by applying Grover's algorithm to a quantum computer, you could retrieve the desired name in only a few seconds. It should be noted, however, that a single outcome obtained from such calculations is only a probable solution. The more times the computer performs the calculations, the more likely it is to find the proper solution to the problem. Quantum computers are devices mainly designed to solve complex problems, which require us to deal with very large amounts of data. These types of machines will soon find a practical application in research laboratories instead of computer games. The role of a quantum computer is to provide assistance in capturing what is beyond the boundary imposed by time and energy needs. Perhaps in the not-so-distant future, we will be able to climb up the ladder to a new rung of possibilities, such as the creation of new drugs, breakthroughs in research on climate change, and the development of new technological devices. It is the hope that these new discoveries will provide us with a deeper understanding of the structure of the reality that surrounds us. And all of this thanks to the laws of nature and the desire to explore, which defines humanity.
Another way quantum computers, another way quantum computers can be better than classical computers. That say you put a classical computer to find a way out of a maze, it has to find its way out one path at a time. A quantum computer can find its way out by taking all the paths at the same time, parallel problem solving.
I'm Jeremy Hilton. I'm the Vice President of Processor Development at D-Wave Systems. I'm responsible for the processor development group, which involves the design, test, and development and release of the quantum processor that D-Wave makes, which is the underpinning of the quantum computers that we build. Each of these black systems is a quantum computer. Inside that system is a thumbnail-sized quantum processor. In order to operate and develop quantum processors, we require a fairly extreme operating environment, which includes ultra-low temperatures and an ultra-low magnetic environment. And to achieve those, we need a fairly large and sophisticated system. The main room behind us houses the quantum processor, and the data racks in the front hold the quantum server, where users can access and program the quantum processor. And the other data racks include the cooling system, which includes pumps and is responsible for the chirping sound you can hear in the background. Inside the room, before we get to the quantum processor, there are many layers of shielding which allow us to create the low noise magnetic environment the chip sits in. If you look inside the data racks, you'll see that they don't contain what you would normally expect. So here we have some scroll pumps, which are mechanical parts associated with pulling vacuum on the fridge inside the room behind. So this is obviously highly unusual for a data rack, but has been integrated so that it wouldn't look out of place in a data center. And in fact, the requirements for running the system are consistent with all the services that would be available in a data center, which would include chilled water and power, predominantly. In this rack is the quantum server, which allows users from anywhere in the world to interact with the processor itself. This server is receiving information from users, converting that into the machine language of the processor, and sending that machine language into the room behind, where high-precision analog electronics will convert those signals into electrical pulses, which are sent through cables into the refrigerator and down through the cooling system to the ultra-low temperature of the processor. It executes this problem, and then data from the processor is returned to the server and returned to the user. And the system is very flexible, and then users can be programming in whatever language they're comfortable with, and in interacting with it, either with this system in their data center or even here in D-Wave's lab. The quantum bits in our processor store information in the form of little magnetic fields. The 0 and 1 correspond to a little magnetic spin. The controls over the qubits are all in the form of magnetic fields. So the quantum processor is very sensitive to magnetic noise in the magnetic environment that it sits in. In order to keep that magnetic environment really low, as well as support the ultra-low temperature that it's operating at, this system behind me has about 16 layers of shielding between where I'm standing and where the chip sits at the center. These black panels are really for aesthetic purposes, and they integrate these data racks with a shielded room, which is the first of those layers of shielding, and is filtering out RF signals. So if you were to stand inside the room and close the door, your cell phone would stop receiving a signal. The fridge itself has a combination of radiation shields as well as magnetic shields, which help support the ultra-low temperature operating environment and achieve the ultra-low magnetic field. Inside the room, we have to keep electromagnetic noise very low. So even things like power outlets aren't allowed, because power can be quite noisy without extensive filtering. So inside the room, we have the cooling system, and these are radiation shields. So this is the next layer of shielding inside the room. The chip itself, the quantum processor, is sitting at the bottom of this array of shields. And this is, again, the first of several more layers. Inside these shields is vacuum, which is the insulation of the cooling system. When we want to swap the processor or conduct maintenance on the fridge, we warm the system up, we remove these shields, and then the processor is accessible, as well as all of the internals of the refrigerator.
customers now. I'm the Director of Professional Services at D-Wave. I talk with our customers and partners about what quantum computers are, what kind of problems that they solve, and work with them to develop software that uses quantum computers. We're standing inside a quantum computer. And you may know that the quantum world is delicate. It's easily disturbed. So there are many layers of shielding in the system, which we've removed in order to look at the internals here. A traditional supercomputer may have many thousands of processors in it, but in this quantum computer, there's only one chip located right down here. When you send an instruction to the quantum computer, a delicate quantum calculation is taking place on that chip to produce your solutions. The system we're looking at here is an ultra-low temperature cryogenic fridge. Because it works at such low temperature, we use the Kelvin scale to measure how cold it's getting. In the Kelvin scale, a warm room is like 300 Kelvin, and 0 Kelvin is the lowest temperature that can be reached. Physicists refer to it as absolute zero. There's two levels of cooling in this system. The top one is a pulse tube refrigerator, which takes us from 300 Kelvin to 50 Kelvin, and then down to 3 Kelvin. This is roughly the temperature of interstellar space. And then a second refrigerator, a dilution refrigerator, takes us in this plate from 0.7 Kelvin, 0.1 Kelvin, and then down to 0.01 Kelvin. When this system is operating, this plate and everything mounted below it is 10,000ths of a degree above absolute zero, which is more than 100 times colder than interstellar space mounted here. And this whole system is designed to sustain those low temperatures in a continuous cycle. When you send an instruction to a quantum computer, the signals pass down these wires along the sides of the refrigerator. And at this point, there's a break in the wires where all the signals become superconducting. Superconductivity is this amazing effect where you can send electrical signals without any resistance whatsoever. So the electrons aren't even interacting with the atoms in the wires around them. That's great because it means that this portion of the system has no energy dissipation, it produces no heat. But it also means that we can't rely on the wires to cool the electrical signals and eliminate their noise. So we have a custom filter bank mounted here which cools those electrons. An important aspect of the superconductivity is that these signals and the quantum processor unit consume virtually no power, whereas the supporting systems around it consume about 15.5 kilowatts. And this remains the same regardless of which processors are installed in the car. If you were to take a fully populated server rack out of a traditional supercomputer, it might consume 10 times that much power. So for our first customer, Lockheed Martin, when they upgraded from their first chip to the D-Wave 2, they saw a relative performance improvement on the order of 10,000 times, but the power consumption for the system was the same.
No more video and we'll be done. After the video is over, you can ask me questions.
Hi, I'm Mark Johnson. I'm a scientist at D-Wave Systems, and I work with a team of other scientists and engineers developing the superconducting integrated circuit chip that's at the core of our quantum annealing processor. We have our chips fabricated on 8-inch silicon wafers, and when we receive them back from the foundry, they look like this. Here, if you look closely, you'll be able to see a repeated array of squares that are multiple copies of our integrated circuit chips. That integrated circuit chip is really just a series of metal layers, predominantly, which you can see in cutaway here. The process that goes into fabricating this integrated circuit chip is actually not that different from that which goes into making the chip that drives your cell phone or your laptop. One of the principal differences, though, is that these metal layers are actually made up predominantly of niobium. And niobium is chosen because it's a superconductor. So the thing about a superconductor is that when you cool it down below a certain temperature, all of the electrons really collapse into the same quantum state. In a sense, they cooperate with each other in the way that electrons in a normal metal don't. Now, ordinarily, quantum mechanics only exhibits on the scale of atoms, electrons, or photons. Superconductors are unique in this way in that you can see quantum behavior on a much larger scale. And it's these properties, these quantum mechanical properties, that enable us to use these materials to make our quantum processor.
So this is a blueprint of one of our processors. The design and construction of one of these is not really that different from that of a conventional processor, but a really important difference is that in a conventional processor, the ones and zeros are encoded as voltages and currents on that chip. In this processor, that information is actually encoded in small magnetic fields called single flux quanta, or quanta of magnetic flux. When we're programming the processor, we load hundreds of thousands of these flux quanta into the chip, into various circuits. Then the processor undergoes this algorithm, quantum annealing, which is how it solves the problem that we pose to it. At the end of that, the answer is in the form also of magnetic flux quanta, which are then pulled out of the processor to the four corners and then up into the room temperature electrons and up to a conventional computer. So the basic computational element in a quantum processor is a qubit. Now, a qubit is a lot like a bit in the sense that it can encode a state as 0 or a 1, but it's a quantum bit, Q for quantum bit, and it has the additional properties that can be in a superposition of 0 and 1 at the same time. So this chip is made up of repeating tiles or unit cells, and each one of them is made up of 8 qubits. Now, if you take one of these unit cells, we can blow it up and get a better view of it here. So our qubits are actually superconducting wire loops that are interrupted with a circuit element called a Josephson junction. And we make our qubits long and thin. You can see that there are 4 of them running vertically here, and another 4 running horizontally here. Wherever these qubits cross or intersect with each other, we put a tunable coupling element that can be used to allow the qubits to influence each other in a programmable way. A qubit is engineered so that there are 2 stable states corresponding to circulating current going clockwise or counterclockwise. And associated with those 2 stable states are magnetic field either coming out of the surface or into the surface. And they correspond to the 0 and the 1 state respectively for the qubit. Of course, a qubit can be in a superposition of 0 and 1. And so in this case, that means that these qubits can be in a superposition of those 2 circulating current states going clockwise and counterclockwise at the same time. So the idea that a macroscopic object like a wire loop could really be in the superposition state, a circulating current going clockwise and counterclockwise, is counterintuitive. It's quite odd. But this is the sort of thing that happens in quantum physics on the microscopic scale. And this is exactly the sort of phenomenon that we're harnessing to make our quantum annealing processor.
Any questions? No? No. That concludes my presentation. Thank you for listening, watching, and see you next time.